Hello class, welcome to Fundamentals of Petroleum. This is our overview class, and today we're going to cover sections 1.1 through 1.2, and that'll be found on pages 9 through 73. So let's get started. Now, the basic concepts of geology is what we're going to study in this chapter. Now, geologists geology deals with the origin, history, and the physical structure of the earth and how it evolved by looking at the rocks. The rocks record the different things that were going on the earth at different times. Now, geologists try to answer questions like how old is the earth, where did the earth come from, what is the earth made of, and how has it changed through times. Now, they study things that happened millions of years ago, such as earthquakes, volcanoes, and they try to get a deeper understanding of how the earth is made and what it's made of. Now, petroleum geologists, they look at rocks that contain oil and gas, and particularly rocks that contain enough to make it worth their while to drill and go and get it. So they try to reconstruct the history and to find areas that are likely to have petroleum reserves in it. When they find these locations, they look at whether it contains enough for the companies to want to go. Now, even experienced oilfield workers refer to a reservoir as an oil pool, but really a petroleum reservoir is not like a lake of oil under the ground. It's really contained in rocks. It's more like a sponge that holds water. Now, when you look at this picture that we have, it's found on page 10. It's the basic concepts of geology. Now, astronomers and physicists and scientists, they believe that the earth was formed 4.55 billion years ago from a cloud of dust, and so gravity pulled all that stuff together, and by it being pulled so tight together, the heavier things went to the middle and the light things stayed on the top, and so it made it the heavier things went to the middle and made the core of the earth. The core is made of two parts: the inner core, which is solid, and then you have the outer core, which is a liquid. Then you have the mantle, which is a solid, and then you have the crust on top, the thing that we're walking on every day, the crust. Now, the crust usually is about, I would say, 10 to 30 miles, 10 to 30 miles thick. And so remember these, the crust, then you have, it's solid, then you have the mantle, it's solid, then you have the outer core, which is liquid, then you have the inner core, which is made of the heavier materials, which is a solid. Now you have on page 11, we're looking at the different forms of plate tectonics. Now, when the earth was first formed, it's believed that all of the land masses was in one spot. And then as the millions of years went by, the different plates or the different continents started to separate. Now, really, if you look at this picture, you can really, I don't know, when I look at it, I say, yeah, I believe that this could have happened. It could have fit right there because you see where it fits. And then also it's breaking off a little bit further, and then this is how it looks today. So when you have these different continents or these plates which float on top of the mantle, and which is floating on top of the outer core, which is on top of the inner core, you'll have those big plates or the continents moving, and that's what's called plate tectonics. Now, oceanic crust is 7 to 10 miles thick. Now, it's really thinner than the continental crust, which is 10 to 30 miles thick. But also, the oceanic crust is made of heavier materials. Maybe they're just more compact. That's why they're not as thick as the continental crust. But when those two crusts collide with each other, the the oceanic crust tends to dip down and go below the continental crust, which is 10 to 30 miles thick. When two plates moving apart, as it is in this picture, you have lava. It's called lava when it comes to the surface, but it's called magma when it's below. And the lava comes underneath and it separates the different plates. And when it pushes them apart, the lava becomes hard and it helps to form more land masses. And so also, as the plates collide, oceanic crust is heavier, so it goes down in this picture. And when these plates collide, they also cause earthquakes and several things like that. You'll find that on, I think that picture is on page 14. Now, when these different plates move and different plates collide and the rocks bend because of the terrific heat, you get two things that are formed, two basic structures that are formed when rocks deform or change shape due to tectonic movement. You get folds and you get faults. We'll cover the folds first. Now, when you look at this fold right here, the first one is called an anticline. That anticline is a fold that comes from the plates pushing together, and it makes the rock bend in an upward slope, in an upward position. Now, when the rock folds or bends in a downward shape, then it's called a syncline. And the other one we're going to look at is a monocline. It's like just a hill, just a slight slope on one side. Now, when you look at those, that comes from the heat. Now, fold is when the rock deforms, but it doesn't break. Now, you also, let's look at these. Domes can be circular or they can be elongated. So when you have a dome that comes up and is perfectly round, that's a circular one. But then if it goes almost like a ridge, but it's high in the middle and it could still be a dome. Just depends on what the structure looks like. Now next you have faults, slips, thrusts, and laterals. So the main thing I want you to remember about a fault is it's a big crack. When those plates move and they hit each other, they make big cracks in the ground. So a fault can be a crack in the ground. It can be a slip, as in A, where it just slipped down, and then a thrust if one part is higher than the other. Now, the difference between this slip and this thrust, when the ground falls down during the fall from where it normally was, it's going to be called a slip. And then when it goes up higher than it normally was, then it's going to be called a thrust. And then when you have the fault or a big crack happens in the ground to where the two parts slide side by side, but one doesn't go higher than the other one, then that's when you have a lateral fault. Now this part, the graben, there are little things that people can remember to try to figure out which one is which, but a graben is when you have two faults and the piece in the middle falls down lower than it normally was. And so that's a graben. And then you have a hoist, which I always say hoist. And then that way I can remember hoist means to lift up. When you have two faults and then the middle part rises up higher than it normally was, that's called a hoist. Now pores are are cavities in rock that holds hydrocarbons. Now when you have these pores contain oil or gas, or should I say hydrocarbons. Now these pores are cavities, and that's good. Most geologists want the rock or the formation to contain at least about 10% pores or porosity, 10% before it'll be viable for them to drill. Also, not only does it have to be porous, but the pores have to be connected. And when the pores in the rock are connected, the rock is said to be permeable. This allows the minerals to flow. So not only does the rock or the formation have to be porous, but it has to be permeable, or it's very difficult to get anything out of it. Now, this is how these structures trap hydrocarbons. That is why they're so important to geologists. If you look at this anticline, it's trapping gas, oil, and then water under the bottom. And then you have a fault trap to where the oil and the gas and the water, they can't go any further than that fault. And then you have one that's, this says unconformity, but it's just saying that it can happen any kind of way. And then you have an impermeable barrier, which means the oil, the gas, and the water were migrating, but then it reached a point in the rock to where it couldn't go anymore. Probably that rock is not porous, or permeable, so it couldn't go any further. Now these traps are traps or they call it trap. They're saying oil trap, gas trap, or petroleum trap. You can say hydrocarbon trap, whatever kind you want to say, but that is why most geologists look toward faults, and so that they can find these traps, and that's where a lot of oil and gas is found. Here's a salt trap to where you have a salt dome here. Now, most of the oil and gas or the minerals are trapped in a dome like this, a salt dome, usually around the bottom part. But in this case, it's some at the top, and then it's even more at the top. This reminds me a lot of the, what is that, the spindle top. They had a lot of oil and gas at the top, but they were drilling down toward the bottom and they were coming up empty. So now gas is the lightest and water is the heaviest. So you'll find the oil in the middle. Now connate water was trapped when the rock was formed. All formations, most formations have connate water, and that water is covering the rocks, and then the oil is on top of them. So each of these pores have somewhat of a bit of connate water. Now wetting water or connate water usually coats the grains of the reservoir rock. The gas is under pressure, and then it expands to provide pressure or drive to push the oil to the surface. So when you think about this gas being under pressure, gas is compressible, just like air compressor. It gives you more pressure, and then as you release the pressure, it expands. Well, liquid doesn't expand, or liquid doesn't compress that well. So when this gas cap pushes down on the oil, when you open the valve at the surface, it allows it to be pushed up to the surface. Pressure, or PSI, underground is about 1/2 pound per foot. So it's like 5.52 pounds per foot. So the deeper you go, you go 2 feet, you add about a pound of pressure. So when we look at this column, to keep this oil in the ground or keep it from blowing out, we have to put a column of fluid or drilling mud to hold the pressure down. Now the artesian effect is on page 41. Now the artesian effect is when you have folds in the formation that allow the water level to be higher than the water at the bottom. So water usually tries to find its own level. So what happens is when you open the valve at the top and relieve the pressure, it's a higher pressure at the bottom. So you get abnormally high pressures when you have the artesian effect, and that helps to drive or push the oil to the surface. A seep is when the oil reaches the surface on its own. You can think about maybe Jed Clampett or something like that. Jed Clampett was shooting for some food, and then he shot the ground and oil came up. So that's a seep. A seep is when you see the oil on the top of the surface without having to do anything. You just walk there and the ground is oily. That may be a good place to start digging for sure. Now, seismic surveys are used to see the boundaries between the rock strata. The strata are those different layers that were formed over thousands, millions of years, and each era has a strata. And then as plate tectonics happen, those strata have bends and folds in them. And so um, they can put seismic waves in the ground to where they can get a printout and they can tell what's under there. Also, they have 3D seismic images, which they can actually see whether hydrocarbons are present under the ground. When you look at this vibrator truck, I would say that the truck thumps the ground and then sensors connected to the recorder trucks picks them up. So they'll put geophones or earth phones, I guess you can say, to listen, and then they have different channels. And the truck, the recorder truck, can tell where the different waves are coming up to the sensor. So when they get this reflection, they can actually tell what's under the ground and where the oil, gas, and the water is. So that's pretty cool. They'll know before they even start drilling what's under there and where it is. Now this vibrator, I guess you can say, look at that in the middle of it. It sends shock waves through the ground. It creates low frequency sound waves, and those geophones pick it up and pick up the reflection of it and can give the operator an indication of what's under the ground. Also, they can do this at sea. They got shock waves from an air gun, and it sends waves out, and the sound reflects off the formation and is picked up by the hydrophones that are being towed behind the ship. Well logs are used to see if there's enough hydrocarbons under the ground where it would be viable for them. These readings, geologists go to school to learn how to read these things. So I can't really tell you which part is, but I know a geologist. I'll ask him how to read this thing. I think the green part is the oil. I believe that is correct. So, but I'll find out and I'll get back with you on it. Now, well cores are used to determine exactly what the formation is made of. They have a specialized drill bit to where they'll drill down, they'll take a core out, and then they'll lay them out and label them. And as they lay them out and label them, they know exactly how deep the different kinds of rock and what's in the rock. They'll analyze it to see what they have under the ground, and they can have a perfect view of what's under the ground, and they can know how deep it is. Well, this ends our slideshow for this section. You can read sections 1.1 and 1.2. I think one of the things that we didn't go over that I'm going to go over in detail on another video is the rock cycle. The rock cycle is very important in your upcoming classes. So I didn't think I'd put it into this one, but I'm going to do a separate one on the rock cycle. So if you have any questions, let me know, and we'll talk to you later. Thanks.